audible and is my screen visible? Can anyone please let me know in the chat? Okay, thank you. So good evening everyone. Welcome to this NPTEL live session for the course Introduction to Machine Learning. My name is Ayan Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. In this live session I will discuss some practice problems on week 12 topics, and I will also try to answer your questions and queries. So if you have any questions or queries regarding any of the topics, you can ask me. We can start solving some practice problems, and after that, if any one of you have any questions, you can ask me. So this is the first question. Generalization error is given by this expression. Epsilon h is the generalization error, which is given by probability of hx is not equal to y, where x and y are coming from D, sampled from D. So what is D in this definition of the generalization error? So that is the question. What is D in this definition of the generalization error? And there are four options. The underlying distribution we are trying to estimate. Option B is a sample of the underlying distribution. Option C is a different distribution that we are trying to estimate the true underlying distribution. And last option is the universe of distributions. Pratik Tiwari says option B, which is a sample of the underlying distribution. Okay. Anyone else? Abhishek Sharma says option C, which is a different distribution that we are trying to estimate the true underlying distribution. Simarpreet Kaur says option C. Okay, so far I have got two options in the chat, B and C. Any other answers? Correct answer is option A, which is the underlying distribution that we are trying to estimate. So D is the distribution from where the data points are coming, and we want to find estimate this distribution only, that how x and y are related, that we can find out if we can find out the underlying distribution of the x and y values. So from that point of view, option A is the correct answer. So as it is generalization error, we are not picking one sample of the underlying distribution and finding out the error from that. That is the training error, that I have the training data, and the training error is just the error or the loss value that we can get from the training samples. But generalization error is also known as the test error. In generalization error, we try to compute what is the error over all possible data points from which the x and y values are coming. So that is why it's called generalization error. It's not just a sample of the distribution but the whole distribution. So that's why option B is not correct, that a sample of the underlying distribution. And option C, two of you have said option C, so which is a different distribution that we are trying to estimate, the true underlying distribution. It's not the different distribution, it is the distribution from where our data points are coming, x and y data points that we have got in the training data set. We try to in generalization error, we try to find out estimate the underlying distribution for that. So it's not a different distribution but the same distribution from where the data points are coming. And option D is certainly not correct, universe of distributions, which doesn't make sense here. So option A is the only correct answer.
Just one question. When you say B is not correct, is that because the word sample is there, right?
Yeah, so in generalization error, error is not for a sample of the distribution but for all possible data points that can be generated from the distribution. That is why it's generalization error. Yeah.
It is error if you spread the distribution. And when we say x and y is sampled from that D.
Yes. No.
When we say a sample of underlying distribution, the whole distribution, and you have taken a sample, that is a base, right? Because
yes. 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 So in generalization we try to estimate, find out the error for all the data points that are possible from that distribution, and not just a sample from the underlying distribution. In case of training error, we only have the training data points or training samples, and in that case that training sample is just a sample of the underlying distribution. But generalization error is for all the data points that can be generated from the distribution, and we are trying to find out what is the error in that case. So not just for a sample but for the whole distribution. So that's why option B is not correct. Now question 2, the hypothesis function obtained by empirical risk minimization is defined by this. So the H is the hypothesis and H hat, this is the hypothesis that minimizes the empirical risk, or this epsilon H is the empirical risk. And if capital H is a class of neural networks, which aspects constitute its space? So what is capital H if in case of neural networks, if we are trying to minimize the empirical risk for neural network, in that case what constitutes the space of the class of neural networks capital H? So there are 4 options, different number of layers, different number of neurons per layer, different values for weights, and different inputs. Suresh Kumar Singh says option C. Balaji says option C. Okay. Any other answers in the chat? Pratik Tiwari says A. Simarpreet Kaur says A. So I've got two different options in the chat. Some of you are saying C, some of you are saying A. Abhishek Sharma says A and B both. Correct answer is option C, different values of the weights. So H is the class of neural networks, and we are trying to find out the H hat hypothesis or the neural network that minimizes this empirical risk epsilon. And so if in case of neural network training, first we fix the architecture of the neural network, that how many hidden layers should be there and how many neurons should be there in every layer. So we don't change the architecture of the neural network while training. In training, we use backpropagation algorithm. So in training, the backpropagation algorithm optimizes the weights, weight values, not the number of neurons or number of layers. So those things have to be fixed before starting the training. And in case of while training, only the weight values are updated in every iteration based on the loss that we get from each of the data points. So in this case, if we use neural networks, the space is all possible values of the weights, that is the space. From that space, the backpropagation algorithm will try to find out the set of weights that minimizes the empirical risk epsilon in this case. So some of you have said A and B. So different number of layers and different number of neurons. So these two things we don't change while training. While training, we just update the weight values. We cannot change the number of layers during the training process in order to minimize the loss value, but we can update the weight values based on the loss that we get from the data points. Is there any doubt in this question? Now question 3. As discussed in the lecture, most of the classifiers minimize the empirical risk. Which among the following is an exceptional case? So most of the algorithms minimize the loss that we get, which is basically the difference between the predicted values and the actual values, which is also called empirical risk. So which of the following algorithms is an exceptional case? There are 5 options: perceptron learning algorithm, artificial neural network, support vector machines, both A and B, and none of the above. Pratik Tiwari says C, SVM, and Suresh Kumar Singh says C. Abhishek Verma is asking, can you please tell us about the exam format? I don't know. So exam questions are generally set by the instructor. So you can ask in the discussion forum. There the regular TAs and the instructors should be able to answer your queries regarding exam format. So we don't have any information about the exam. Dr. S. Radhakrishnan says option D, A and B. Balaji says D. Okay, so I've got 2 C's and Kameshwar Panda also says D. So 3 D's I have got in the chat. Any other answers? The correct answer is option C, support vector machines. So in case of most of the machine learning algorithms, we try to minimize the empirical risk or basically the loss value. Different loss values are used in different algorithms, but overall it's the empirical risk, and in almost every algorithm we minimize the empirical risk. But in case of support vector machines, we don't directly minimize the empirical risk or the loss value. Here we maximize the margin. So we get we have 2 sets of points like this, and we try to find out the linear separator which maximizes the margin, that is the distance between the this linear separator or straight line and the nearest points from both the sets of data points, both the classes. So we try to maximize this margin. This is the margin, this distance is the margin. So in case of SVM, we try to find out the linear separator that is that maximizes this margin, or which is almost equally distant from both sets of points, positive points and negative points. So we don't directly minimize the empirical risk, although by maximizing the margin, it actually minimizes the overall loss value or the error value, but we don't minimize the empirical risk or loss value directly. We maximize the margin in case of SVM. So this is why SVM is the only correct answer. So in perceptron learning algorithm, in every iteration we compute the predicted values and then we subtract it from the actual values, and based on that we find the derivative and update. And the same thing happens in case of artificial neural network. So in case of neural networks, we use backpropagation, which again computes the error values, which is basically the difference between the actual values and predicted values, and based on that the weight values are updated by using the derivatives of those weight values, derivative of the loss function with respect to the weight values. So again the empirical risk is minimized. But in case of support vector machine, this is not the case. So that's why this is the only correct option here. Question 4. What happens when your model complexity, such as interaction terms in case of neural networks, order of polynomials in case of SVM increases? So what happens when your model complexity increases? So model complexity may be different parameters in case of different machine learning algorithms. So if the model complexity increases, what will happen? And multiple options may be correct here. Model bias increases, model bias decreases, variance of the model increases, variance of the model decreases. So multiple options may be correct here. So I've got many answers in the chat. Pratik Tiwari is saying B, C, Balaji says A, Aditya says A, D, Suresh Kumar says B, C, Balaji says A, C, Dr. S. Radhakrishnan says A, D, Anandan says A, C, Dr. Radhakrishnan again says A, C, Simarpreet Kaur says B, C, Pandyan says BC. So most of you are saying BC, some of you are saying AD, AC also. Kameswar Panda says AD. Correct answers are B and C. So two options are correct here. Many of you have already said B and C. So if model complexity increases, we know that it is overfitting. If model complexity increases, it becomes much more prone to overfitting, and in case of overfitting, bias will decrease, but the variance of the model will increase. Because bias is simply the error or basically the training error. So if you make your model much more complex, it will be able to reduce the training error further, which is better, but the variance of the model increases along with that. And in case of underfitting, bias increases and variance decreases. So those two are two contrasting things, underfitting and overfitting. So in this case, it is the case of overfitting because you are increasing the model complexity. So B and C are the two correct answers. Model bias decreases and variance of the model increases. Question 5. Aliens challenge you to a complex game that no human has ever seen before. They give you time to learn the game and develop strategies before the final showdown. You choose to use machine learning because an intelligent machine is your only hope. What is the machine learning paradigm should you choose for this? Option A is supervised learning, option B is unsupervised learning, option C is reinforcement learning, option D is use a random number generator and hope for the best. So all of you are seeing option C in the chat so far. 6 answers I am getting from the chat. All options are C. Correct answer is option C. So all of you have written the correct answer in the chat. So it says that the game has not been played by humans before, so you don't know about the game, so you don't have any expert output values that you can use in case of unsupervised in case of supervised learning. So in supervised learning we need labeled data where you both have the input values and the output values. So you don't have that expert output values, so you cannot use that. But in case of reinforcement learning, you don't need those output values immediately. You can interact with the environment. In this case, the game is the environment, so you can interact with the simulator or the environment, and from the environment, based on your actions, you can get reward signals or penalties from the environment, and based on that you can update your policy or actions at given at states. So that's why reinforcement learning is the best choice in this case. So reinforcement learning is optimal for building agents for complex games where no expert trajectories exist. So if expert trajectories exist, then in that case supervised learning can be used comfortably, but in this case the game has not been played before, so reinforcement learning is the only option here. Question C. In the Pavlov's dog experiment, what is the input signal to the dog and what is the reward? So I hope all of you know Pavlov's dog experiment. In that case, what is the input signal and what is the reward? So basically there are four options: bell, digestion, food, praise, food, digestion, bell and food. Balaji says option D, Simaprit Kaur says option D, Kameswar Panda says D, Pratik Tiwari says D, Suresh Kumar Singh says D, Dr. S. Radhakrishnan says D. So all of you are saying D. Anandan says D. Mani Bharati says D. Okay. So all of you have already said option D, and D is the correct answer. So the Pavlov's dog experiment is the setup of this experiment is very similar to what we do in case of reinforcement learning. So the input signal given to the dog is bell, and the reward that the dog gets is food, which is also similar to in reinforcement learning. So at a given state, if you take a certain action, you get some reward from the environment. So based on that action, you can get either a reward or a penalty, and also rewards can vary. The value of the reward can also vary. So that's why the setup is very similar to reinforcement learning. And the input signal is bell, and the reward is food. Option D is the correct answer. Which of the following measure best analyze the performance of a classifier? So different evaluation measures are given in the option: precision, recall, accuracy, time complexity, and depends on the application. Balaji says A, Pratik Tiwari says E, Suresh Kumar Singh says E, Shankar Lal says E. Any other answers? Mani Bharati says E. Question number
three.
3. Yeah, after this question I will go to question.
I just want to write it. Take
Yeah.
this.
You can get all these slides in the NPTEL portal. The lecture links to the lectures, these live session lectures are also there, and these PDFs are also there, links to these PDFs. So the correct answer is option E. It depends on the application. So generally we use accuracy in many of the applications, but that might not be applicable in some cases, like in critical domains like health and security, where the number of positive samples are much lesser than the number of negative samples. Their recall is much more preferred, and in some cases precision is preferred. Precision is generally preferred in case of information retrieval applications. So even though generally we use accuracy, but it might not be the most applicable or most appropriate performance measure for all the tasks. So it depends on the application. Option E would be the correct answer. So if there is imbalance in the dataset based for the classes, in that case accuracy is not the best option. So either it's precision or recall, or in some of the cases F1 measure is also used, F1 score. Option A is the correct answer. With question 3. Yeah, this is the question 3. Oh, sorry, 4.
Second, the area network question. I have this one question, short question.
Which one? This one.
Yes, on the website. So I just want to know if the hypothesis in this underlying distribution is where you get the normal weights to assign normal weights. Right?
Yes.
Right. What will be the hypothesis?
What will be the hypothesis?
Yeah, hypothesis, classic hypothesis.
I'm not able to hear you properly. There are some noises coming, so.
I will ask later. I will ask.
Yeah, okay. At the end of the practice problem session, you can ask. Now, question 8. Yeah. Suppose we want an RL agent, RL is reinforcement learning, to learn to play the game of golf. For training purposes, we make use of a golf simulator program. Assume that the original reward distribution gives a reward of plus 10 when the golf ball is hit into the hole, and minus 1 for all other transitions. To aid the agent's learning process, we propose to give an additional reward of plus 3 whenever the ball is within the 1 meter radius of the hole. Is this additional reward a good idea or not? Why? So the original reward is that the agent will get plus 10 if the ball goes into the hole, and minus 1 for all other transitions, and an artificial reward is added that whenever the ball is within the 1 meter radius of the hole, plus 3 award will be given to the agent. So that is an additional reward on the top of this plus 10 and minus 1 rewards. So is this a good idea of having this additional reward of plus 3? Sure. There are 4 options. Yes, the additional reward will help speed up learning. Second option is yes, getting the ball into a meter of the hole is like a sub goal and hence should be rewarded. Option C is no, the additional reward may actually hinder learning. And last option is no, it violates the idea that a goal must be outside the agent's direct control. Okay, so many of you are saying option C. Pratik, Shankarlal, Simarpreet, Suresh Kumar Singh, all are saying Abhishek Sharma. All of you are saying option C, and then Mani Bharati, Kameshwar Panda, and Dr. S. Radhakrishnan are saying option B. Balaji is saying option A. Anandar is saying option C. And the correct answer is option C. So most of you have written the correct answer in the chat. So original reward distribution is +1 for hitting into the hole and -1 for all other transitions, so that it hits the ball into the hole faster. That's why this -1 is given for every time step, other than putting it into the hole, which gets +10. So if this additional reward of +3 is given whenever the ball is within the 1 meter radius, it might happen if exploration is not done properly, that the agent will only learn to get the ball inside this 1 meter radius of the hole, and it will not be able to learn that by hitting the ball into the hole it will get +10 reward. So it will just accumulate a reward by getting the ball into the 1 meter radius, and it will not learn to put the ball actually into the hole, which would get +10. It would not learn that, so it would hinder the learning process. So that's why the original reward distribution is much better than adding this additional one. So the additional one might also work, but in some cases if the state space or the state action space is not explored properly, it will not learn to put the ball into the hole. It will just get the ball inside the 1 meter radius, because even in that case it gets +3 reward, so it will not learn that it will get a +10 if the ball is hit into the hole. So that's why option C is the correct answer. Now question. Yes.
Like when for different cases when people addition towards the right? I mean, what our addition?
In some applications, if the reward function is very sparse, that after 50 or 100 time steps you get a positive reward, and before that you get 0 reward. So it doesn't have any reward signal till you get to the goal. In this case, goal is the hole. So in that case you might want to direct the agent towards the goal by giving some small positive rewards that would lead the agent towards the goal. So if the reward is very sparse, basically, in that case you might want to give some small rewards along the path. And if the reward is not very sparse, in that case it would hinder the learning process, because if the reward is very sparse, let's say after 100 time steps it reaches the goal, so it might never be able to reach that goal. So it will not learn that it can go to the hole at some point. So in that case small rewards can be given along the path that might direct the agent towards the goal state.
It can be multiple of like multiple small.
Yes, I mean, in this case of in this case, yeah, in case of golf, this reward function might be sparse, might be dense, depending on how many time steps you require to put the ball into the hole. But in some cases, there might be some sub goals, and first you visit those sub goal states and then visit the goal state. In that case, by visiting the sub goal state, you might give the agent some small rewards to encourage it exploring those the state space. So in this case it might not be a good idea, but in case of some other applications it might be a good idea to give it some small rewards in order to encourage it to explore the state space further. Now question 9, what type of feedback does an agent in reinforcement learning receive? Predictions, labels, clusters, rewards or penalties? So I have got many answers in the chat. This is a very easy question. So all of you are saying option D. So all the answers are option D in the chat. Yes, so the correct answer is option D. So it gets rewards or penalties from the environment as a feedback for its action that the agent has taken at a given state. So option D is the correct answer. Now question 10. You are designing a reinforcement learning agent for a racing game. Among the following reward schemes, which one leads to the best performance of the agent? So you have to find out the best reward scheme that would lead the agent to the best performance in the racing game. First option is +5 for reaching the final line and -1 for going off the road. +5 for reaching the finish line, -0.1 for every second that passes before the agent reaches the finish line. +5 for reaching the finish line, -0.1 every second that passes before the agent reaches the finish line, and +1 for the agent going off the road. And -5 for reaching the finish line, +0.1 for every second that passes before the agent reaches the finish line. So which is the best reward scheme? So Pratik Tiwari says option B, Shankar Lal says B, Suresh Kumar Singh says B, Simarpreet says B, Balaji says B, Dr. S. Radhakrishnan says A, Kameshwar Panda says C, Anandan says B, Mani Bharati says B. Okay, so I've got many different answers in the chat. Some of you are saying most of you are saying B, but some options are also A, C. Correct answer is option B. So plus 5 for reaching the finish line is very obvious that you need to give a high positive reward once it finishes the race. So plus 5 would be given to the agent for reaching the finish line. But as it is a racing game, we need some sort of reward so that the agent learns that by finishing the overall episode faster, it gets more reward. So you need to give some penalty for every second before reaching the final line, finish line. So that would encourage the agent to finish it faster. So that's why this minus 0.1 for every second, it should be very small for every second, because for every second you are giving this reward, it should be very small, that compared to the total positive reward that will be given at the end, which is plus 5 in this case. So this minus 0.1 for every second that passes before the agent reaches the finish line. So these are the two different reward signals that would be given to the agent. And some of you were saying A, that minus 1 for going off the road. So that might also be implemented, but the option A doesn't have this penalty, small penalty for every second before the agent reaches the finish line. This is important because it's a racing game. We want the agent to reach the finish line faster, which can be obtained by giving a very small penalty for every second. So that's why option B is the correct answer here. Now question 11. You want to create a self-driving car software in the context of standard reinforcement learning framework. What would you classify as state and actions? Note that your system does not have access to previous states, so it's based on only the current state the agent to take the action. So what are the things that you need to put in the state, and what are the things that you need to put into the action space for a self-driving car? So option A says state should contain current steering wheel position, current pedal position, current speed. Action should contain turn steering wheel, press pedals. Option B says state should contain current steering wheel position, current pedal positions, current acceleration. Action should contain turn the steering wheel and press pedals. Third option is state should contain current steering wheel position, current pedal position, current speed, and action will be change direction and change speed. And fourth option is state should contain current steering wheel position, current pedal positions, current acceleration, and actions should contain current direction and change direction and change speed should be there in the actions. So which of these options would be best for the state space and the action space in case of self-driving car? Pratik Tiwari says A, Shankar Lal says A, Simarpreet Kaur says A, Suresh Kumar Singh says A, Kameshwar Panda says A. Balaji says A, and Dr. Radhakrishnan says option C. Anandan says A. So most of you are saying A. Yeah, most of you are saying A. Anyone else? So correct answer is option A. So most of you have written the correct answer in the chat. So the state space should contain all the features that are required to make the decision at that point. So it should contain all the things that I need to take into account to take an action. So we need to know what is the current steering wheel position, we need to know the current pedal position and the current speed. So these are the three things. If we know these three things, we can take an action, and the action should contain all the necessary things that will change the state. So that makes the state transition possible. So there are two things that will be in the action space: turn the steering wheel and press pedal. So by turning the steering wheel, we are changing the direction, and by pressing the pedals, we are changing the speed. So that's why these two things need to be there in the action space. But option B says that the only thing that is different in option B is the current acceleration. But even if you know the current acceleration, you can't take the optimal action, because action depends on what is the current speed. So based on that, whether you will decide whether you will press the pedal or not based on the current speed, but not based on what is the current acceleration. So you might keep the current acceleration in the state space, but current speed is much more important to put in the state to make a decision. Current acceleration is not that much important, so that's why option B is not correct. And option C, I have got one answer in the chat as option C. In option C, the state space is same as option A, but actions are different: change direction and change speed. So change direction is not the exact action that can be taken. The action is the action is turning the steering wheel. So by turning the steering wheel, the direction would change. So the actual action is turning the steering wheel, and similarly change speed is the other action in case of option C. So we cannot directly change the speed, we can press the pedals, accelerator or brake, and by pressing those pedals we can change the speed. So changing speed is not the direct action is pressing the pedals. So that's why option C is slightly different from option A, and option C is not the correct answer. And now question 12. Which of the classifiers do not require any additional modifications to use them when we have more than two classes? Multiple options may be correct here. So generally most of the algorithms are first taught in the class for only two classes, but if we want to extend the algorithm for multiple classes, for more than two classes, we might need some additional modifications to this algorithm. But in some algorithms it is almost inbuilt into the algorithm. We don't have to do anything to apply that algorithm on applications where there are more than two classes. So there are four options: decision trees, linear classifiers, support vector machines, and k nearest neighbor. So multiple options may be correct here. Pratik Tiwari says A and D, Shankar Lal says A and D, Simaprit Kaur says A and D, Suresh Kumar Singh says A and D, Anandan says A and D, Mishti Pandey says A and D, Kamaswar Panda says A, D, Dr. S. Radhakrishnan says A and D. And the correct answers are A and D. So in case of decision trees, we use the cross entropy or the entropy value, and then we compute the information gain. So which is same for 2 classes or 100 classes. We don't have to make any modifications to the formulation of the problem. So decision tree can be applied for more than 2 classes very easily. We don't have to do anything extra. And in k nearest neighbors, it just picks the k nearest neighboring points from the training dataset and finds the in case of regression it finds out the average of the k nearest neighbors, or in case of classifier it just finds out the dominant class in among those k nearest neighbor points. So you don't have to do anything for more than 2 classes, same for 2 classes or 3 classes or 4 classes. But in case of linear classifier, you have to change the algorithm a bit, because now instead of just one output unit 0 1, you need to have multiple output units, and based on that the loss function would also change. So you have to make certain modifications to the linear classifier for more than 2 classes. And for support vector machines, again the general formulation that is taught in the class is for 2 classes, +1 and -1. These are the 2 class levels. So now if you have multiple classes, then you have to modify the algorithm, or some other techniques are also there for handling multiple classes. In case of SVM, one versus all method is also used in case of SVM. So additional modifications are required also in SVM, but in case of decision trees and k nearest neighbors, no additional modifications are required to apply them for more than 1 classes. So these were the practice problems that I wanted to discuss in this live session. So now if you have any doubts or questions regarding any of the problems discussed in this live session, you can ask me. Second question. Yes.
So I just want if you can sorry, if you can explain that X bigger that we call the classified hypothesis when we apply neural network.
Yes.
So yeah, so basically you can explain in calculate this
So yeah, in this case, for neural networks, first we fix the architecture. We don't change the architecture during the training process. So number of layers and number of neurons are fixed beforehand, and during the training process we just update the weight values, isn't it? So the class of neural networks that is available to us during the training is which is H here, is the class of neural networks, is basically the all possible values for all the weights, and from that set we try to pick the set of weights that minimizes the risk, empirical risk. So we don't change the number of layers or number of neurons, so that is not part of the search space H. So only the set of weight values are part of H.
that is clear. Like we say we are have a large underlying distribution where we take values of weights in a single neural right? Then we say there is this hypothesis error. If I apply that weight,
Yes.
I calculate some error on that.
Yes.
Right?
Yes.
So how it is a class of hypothesis? Like class of hypothesis is like when we say all the errors that you make on the weights.
The class of hypothesis, so this H class of hypothesis would contain H1, H2, like this. It can be infinite. So H1 is for one set of weight values, H2 is for one set of H values, H3 would be for another set of H values, like this, weight values. So for different weight values we will get a different hypothesis. So H would be infinite in this case because weight values are continuous. So you get an infinite set. So from that infinite set you try to find out the H hat from this set, which minimizes the empirical risk. So every hypothesis is for a different weight value. As weight values are continuous, obviously this search space would be search space would be infinite. Size of the search space would be infinite. So from that search space we try to find out the set of values which will be H hat, which minimizes the empirical risk. Any other questions? Question 1 is saying, Ananda. Yeah, this is the question 1. Yes.
So yeah, there is this in the lecture video. There is this statement like the actually union bond. When we apply union bond in like this on the this term of optic inequality, when we applied it for all the five coordinates term of inequality. So in that, this one statement that you mentioned, like a union bond means that one of them getting a higher energy. I mean, all all the probabilities, and one of them gives a higher. Why is that? Because while we are trying to prove that formula for one hypothesis, like taking HIS comes to taking one analysis, fixing one analysis, and looking at that, and after that we apply method so that we can generalize it for all the networks. And when you apply human bond, we say that they will express at least one of them that will become higher
Hmm.
error. I'm just
No, I don't exactly remember what was in the lecture or what was said in the lecture. So I have to go through that lecture again in that case. So it would be better if you ask in the discussion forum. The regular TAs would be able to answer your query because I don't exactly remember what was said on that Charnov opt-in. Uh,
okay. Taking the next question, the union bond, how that all the probabilities has a probability
it would be difficult to go through that again. It would be better if you go through the video lectures again and ask in the discussion forum because that is quite vast. The learning theory part is quite vast, so uh, I won't be able to work out that thing right now. I also have to go through the material again to do that.
Good evening, sir. So I have a question regarding this
Yes.
regarding this question only. Here we are considering epsilon h, that is L function.
Yes.
Um, but if we consider epsilon hat function,
Hmm.
so in that case, what might be the changes in the answer?
Yeah, epsilon. Yeah, so this epsilon h is the generalization error, but epsilon hat h, so this is the error for the sample that you have. So that is the training error that you can say. So that is for this sample that you have of the underlying distribution. So the answer would change in that case. Yeah. So for generalization error, it is the underlying distribution that we are trying to estimate d. But in case of epsilon hat h, which is the error for the sample that you have. So in that case, it's only the d would be only the sample. So answer would be different. You are right in that case.
Yes.
So if there are no other questions or queries, then we can end this live session here. Thank you everyone for joining. Thank you everyone.